In this video, we are continuing our discussion of improper integrals. If you remember, there's actually two different ways you can have an improper integral, one of which we've already discussed, one of which we've already talked about. If your interval is infinitely long, then it would be called an improper integral. Typically, we expect definite integrals to go from 2 to 7 or 0 to 10 or something like that. But if it goes from 2 to infinity, well, then it would be called improper. So that's where this word is coming from. And so if you have an infinity in the upper limit or negative infinity in the lower limit, it would be called an improper integral. We've already discussed these. That's not the primary point of this video. In this video, we're focusing more on the second type. If you have not just a discontinuity in your interval, but specifically an infinite discontinuity like a vertical asymptote, then this would also be called an improper integral, right? So if you're integrating, even from 2 to 7, let's say, but at 7, if there's a vertical asymptote, then unfortunately you can't use the fundamental theorem of calculus, because the criteria for that to compute the area under a curve require that you be on a closed interval and the function be continuous. And that those would be violated if you had an infinite discontinuity, unfortunately. But fortunately for us, we have a way around this small issue. So let's take a look at what we would do. Okay, so let's see here. Let's assume that your function is continuous on almost the entire interval from A up to but not including B, right? So this would be the situation if you had a vertical asymptote. You see it's continuous from A up to but not including B because of the asymptote. So let's say we have an infinite discontinuity over here at B. So I know exactly what I want. What I want is this right here in green. I want the area under the curve from A to B. That's what this notation means right here. But unfortunately, like I said earlier, you cannot, and don't write this, I'm going to erase this. You can't take the antiderivative of little f and then pop in A and pop in B and subtract like we're accustomed to doing, again, because this is not continuous at B. What we're trying to use is the fundamental theorem of calculus, but you're just not allowed to. It violates the conditions of the fundamental theorem of calculus. So here's what we're going to do. We're going to be smart about it. We're going to integrate from A, but up to a chosen point right before B. We'll call it like C or something like that. So we're going to integrate and find this orange area. If you see my graph here, I'm going to find the orange area. Now I know this isn't exactly what I'm looking for. I have some adjustments to make, but watch this. We'll go take the integral from A only up to C of f of x dx. Now, the fundamental theorem of calculus can be used on this guy because this is a closed interval and it is continuous on the entire closed interval as long as I stop C just short of the asymptote. But now you have this issue though. We fixed one problem, but we created another. What about this leftover area, right here at the tail end? That's a small problem. Well, A is a known number, but C is going to stay just a generic letter C. It's going to be some fixed constant. You can do the integration with that fixed C value, but your answer will have C's, right? Because when you take the antiderivative, you plug in C, you plug in A, and you subtract, your answers will have C in there. So what we do for the last step is when we're done, we'll take the limit and let C push its way on out to B from the left. And what that'll wind up doing is filling in the last little part of the area up to the asymptote. So it's a very smart idea. Now I could write out a similar situation if the asymptote happened at A or so on and so forth. I think this will suffice. You might have to adjust some things if the asymptote was at A instead of B, but I think you should be able to do that. If that was the situation, you would go from C up to B and then let C push its way left to the asymptote from the right of A if the asymptote was at A instead of B. But anyway, this is the generic idea here. So let's try an example. Here we go. Let's say we have the integral from 0 up to 2 for 1 over the square root of x. Now we can already tell we have a vertical asymptote at x equals 0, because that would give you division by 0 right here. So if the asymptote is happening at 0, if this is where the problem lies, then we're going to modify this integral. We're not going to integrate from 0 up to 2. We're going to integrate from, it doesn't matter the letter A, B, C, whatever. We'll just say from A up to 2. Okay, from A up to 2 of 1 over square root of x dx. Okay, now this answer will have a's in it. It'll have some numbers because of the 2, but it'll also have some a's in it. So after I'm done, then I'm going to take the limit where a pushes its way onto 0 from the right hand side of 0. All right, so let's see if we can compute this algebra here. This would be better considered as x to the negative 1/2, to help us integrate, so we can use the power rule. Integral of this would be 2x to the positive 1/2. That's the power rule. Bracket from a to 2, and we'll take the limit as a goes to 0 from the right. Okay, I'll come up here so we can finish it. This will be the limit as a goes to 0 from the right. If you plug in a 2, you would have 2 root 2, right? 2 times 2 to the 1/2. And then we'd have minus 2 times the square root of a, right? 2 times a to the 1/2, basically. All right, so we have this quantity here, but again, this has a's in it. This is if you chose a value just after 0, like 0.1 or 0.2 or 0.05 or something like that. But now that we're done, I need to let that a push its way on out to the 0 for where it should have started. So let's take the limit as a goes to 0, and it looks like as a goes to 0, this term will go away, and so your final answer would be 2 root 2. Okay, so that's the general idea. We see what we're doing here. If we have an asymptote, then you make up an integral that starts at your starting point but goes right up to the vertical asymptote, and then do the definite integral, fundamental theorem of calculus. And then when you're done, then take a limit where that constant, that fixed constant, pushes its way on out to the vertical asymptote the remainder of the way.